When we studied the kinematics of rigid bodies, we saw that rigid bodies can be considered as special systems of point masses for which the laws of conservation of momentum and angular momentum hold. These laws completely determine the motion of a rigid body, since they can be described by the second-order differential equations of 6 scalar variables, that is, the components of the momentum and the angular momentum of the body, and the free motion of a rigid body has just 6 degrees of freedom associated with the translation and the rotation of the body in space. The motion of a rigid body, for example a devil's stick thrown in the air, is generally the composition of a translational motion and a rotational motion. In most of the cases the analysis of such a motion is very complicated. We will therefore consider only some special motions. We do not examine translational motion since it can be considered as a part of the mechanics of point masses due to the law of center of mass. We will only deal with rotational motion, starting with its simplest case, the rotation of a rigid body about a fixed axis. Let us choose the z-axis as the axis of rotation of a rigid body and let phi denote the angle of rotation about the axis measured between the points P and P' in space. Because the angular velocity vector omega is aligned with the axis of rotation, its length is equal to its z component. We already saw that the z component of the angular momentum L of the body with respect to the z-axis is given by the moment of inertia I of the body with respect to the axis of rotation, times the z component of the angular velocity vector omega of the rotating body. The moment of inertia I of the body can be approximated by the sum of n mass elements mi of the body, times the square their distances di from the axis of rotation from I equals 1 to n, where n tends to infinity. The distance di of a mass element at the point Pi can be determined from the length of the position vector r pointing from a reference point O on the z-axis to the point P, and the z-coordinate of the point A if the origin of the z-axis is at the point O on the axis. By applying the definition of the angular velocity omega, the z component of the angular momentum L can be written as the moment of inertia I, times the derivative of the rotation angle phi with respect to the time t. Then the law of conservation of angular momentum states that the derivative of Lz, that is the time derivative of I times omega z, is equal to the z component of the torque with respect to the axis of rotation produced by the net force of all the external forces acting on the body. Here the external forces consist of the free forces exerted on the body which are given, and the constrained forces keeping the axis of rotation fixed which are unknown. Nevertheless, we can assume that the constrained forces are exerted at the fixed axis of rotation and the torque produced by them vanishes. As a result, tau z in the right-hand side of the differential equation is the z component of the torque produced by the free external forces acting on the body. Because the moment of inertia I of the body does not depend on time, we can write the left-hand side of the equation as I times the time derivative of omega z, that is I times the second-order time derivative of the angle of rotation phi. Here the second-order time derivative of the angle of rotation is the angular acceleration alpha of the rotating body. Then we conclude that the equation of motion of a rigid body rotating about a fixed axis is the following. The moment of inertia I of the body with respect to its axis of rotation times the second-order derivative of its angle of rotation phi about the axis with respect to the time t, is equal to the z component of the torque produced by the free external forces acting on the body. This equation is formally equivalent to the equation of motion of a mass point m along a straight line chosen as the x-axis, which states that the mass m times the second-order derivative of the displacement x of the point mass along the line with respect to the time t, is equal to the x component of the force F acting on the point mass. Let us discuss some special cases of rigid rotation here. If the right-hand side of the equation of motion of a rotating rigid body about a fixed axis is equal to 0, that is the z component of the torque tau vanishes, then in the simplest case the time derivative of the rotation angle phi, that is the z component of the angular velocity omega, is constant. In other words, if the torque produced by the free external forces acting on a rigid body vanishes, then the body rotates at a constant angular velocity about its fixed axis of rotation. Indeed, if a flywheel of large moment of inertia, which has a vertical axle with ball bearings holding it in its position, is set in motion by hands, then the angular velocity of the spinning wheel is almost constant. The slow decrease in its velocity is due to the torque produced by the frictional forces between the axle of the flywheel and the ball bearings. If we impose the initial condition such that we measure the angle of rotation phi from the initial angle of the orientation of the rigid body, that is the initial angle phi naught, is 0, then the integration of the first-order differential equations gives the angle phi as the product of the angular velocity omega z of the rotation and the time t. By comparing this result with the equation stating that the distance s covered by a point mass moving along the x-axis at a constant velocity vx is equal to vx times the time t, we can state that the rotation of a rigid body at a constant angular velocity about a fixed axis corresponds to the uniform motion of a point mass along a straight line. Another simple case is when the z component of the torque tau is constant, that is, the angular acceleration of the rotating body is constant. Then the equation of motion can be written in the form stating that the second-order time derivative of the angle phi, which is also equal to the angular acceleration alpha, is given by the ratio of tau z and the moment of inertia I. Because the right-hand side is constant, we talk about a uniformly accelerating rotation of the body, stating that if the torque produced by the free external forces acting on a rigid body is constant, then the body rotates with a uniform angular acceleration about its fixed axis of rotation. For the initial values of vanishing angle phi and angular velocity omega at the initial time t0, the integration of the equation of motion gives an expression stating that the time derivative of the angle phi is equal to alpha times the time t. By integrating this equation, we obtain an expression for the angle of rotation, where phi is given by 1 over 2 times alpha times t squared, that is 1 over 2 times the ratio of tau z to I, times t squared. This solution shows that the equation of motion for a rigid body rotating with a uniform angular acceleration about a fixed axis is formally equivalent to the equation of motion for the uniformly accelerating rectilinear motion of a point mass, where the later tells us that the distance s covered by the point mass is equal to 1 over 2 times the acceleration a of the point mass times the square of the time t. We can study the uniformly accelerating rotation in an experiment by using an apparatus, where two disks of mass md are attached to a horizontal rod and the middle of the rod is joined with an axle mounted on supports allowing its rotation about a vertical axis. The distance between the disks and the axis of rotation is denoted by d. A thread is tightly wound around a pool of radius are attached to the vertical axle, and it passes over a fixed pulley with its end tied to the weight G of mass m held at a fixed position. The weight G acting on its support is given by its mass m times the gravitational acceleration g. Another spool of radius 2 times r is also attached to the axle under the first spool, which can also be used in the experiment. If we set the weight G free by removing its support, then the falling weight will drive the spool fixed on the axle and the system of the disks, and the rod starts to rotate. We can measure the time t1 taken to the first complete rotation of the system, that is when its angle of rotation is equal to 2 pi. Then we will find that during the time intervals 2 times t1, 3 times t1 and so on, the system performs 4, 9 and so on complete rotation, as seen in the table where the duration of motion shown in the first line and the second one contains the number of rotations n of the system during the time 2 times t1, 3 times t1 and so on. This result demonstrates that the angle of rotation phi is directly proportional to the square of the time t, that is, the system performs a uniformly accelerating rotation. The torque is produced on the system by the force F, which has the same magnitude as the weight G, since the fixed pulley simply redirects the force G applied on the thread by the falling weight. As a result, tau z is equal to the product of the magnitude of the weight G and the radius r of the first spool on the axle. If we use the second spool of radius 2 times the radius r, then we double the torque driving the system, which also doubles the angular acceleration alpha of the system. If we do not change the torque and it remains constant, but we increase the distance d of the disks from the axis of rotation to 2 times d, then the moment of inertia of the rotating system becomes about 4 times its original value. As a result, the angular velocity of the rotation reduces to about the quarter of its original value. Now we determine the energy of a rotating rigid body about a fixed axis. The kinetic energy of a rigid body of mass m approximated by a system of n point masses mi is given by the sum of the kinetic energies of the individual point masses, that is 1 over 2 times the sum of the mass mi times the square of the velocity vi of the point mass mi from I equals 1 to n. This formula describes the general case, and if we consider rigid rotation, that is where each point mass approximating the rigid body has the same angular velocity about the z-axis, then we can write the velocity vi of the point mass I as the product of its distance di from the axis of rotation times the angular velocity omega of the point mass about the z-axis. For the sake of brevity, we drop the index z of omega, since the angular velocity vector pointing in the direction of the z-axis has vanishing components in the x and y directions. By substituting this relation into the general formula of the kinetic energy, we obtain an expression stating that the kinetic energy is equal to 1 over 2 times the sum of the product of mi and di squared from I equals 1 to n, times omega squared. Here we recognize the sum as the moment of inertia I of the body with respect to the fixed axis of rotation. Then we can introduce the rotational energy of a rigid body rotating about a fixed axis defined by 1 over 2 times the moment of inertia I with respect to the axis of rotation, times the angular velocity omega of the rotation. Because the center of mass of the body does not perform translation in the case of the rotation about a fixed axis, the kinetic energy of the rigid body is equal to its rotational energy. We also present another important relation for rigid rotation, stating that the work delta W done on the rigid body rotating through a small angle delta phi about the z-axis is equal to the z component of the torque tau produced by the free external forces acting on the body, times the angle delta phi. The infinitesimal version of this formula tells us that the differential of the work W done on the body rotating through an infinitesimal angle d phi is given by the product of tau z and d phi. Now we can apply the work-energy theorem for the experiment producing an uniformly accelerating rotation of the system of two disks attached to a rod. The theorem states that the change in the kinetic energy of the complete apparatus in the experiment is equal to the work done by the weight g after it is set free. When we set the weight G free and it covers the distance z during the time t, the work done by the moving weight is equal to G times the distance z, or the mass m of the weight times the gravitational acceleration g times z. The increase in the kinetic energy of the rotating system and the moving weight is given by 1/2 times the moment of inertia I of the rotating system times its angular velocity omega at the time t, plus 1/2 times the mass m times the square of the velocity v of the weight at the time t. Here we suppose that the mass of the pulley is very small and its moment of inertia is negligible. Then the expression described here must be equal to the work done by the weight, as shown by this equation. Here the velocity v of the weight is equal to the time derivative of its z-coordinate, which can be inserted into the derivative of the whole equation with respect to the time t. Then we obtain the equation stating that I times omega times the time derivative of omega, plus m times v times the time derivative of v, is equal to m times g times v. We can assume that the angular velocity of the rotating system is given by the ratio of the velocity of the weight to the radius of the spool driven by the moving weight, that is, the velocity v is equal to the radius or times the angular velocity omega. We can also replace the product of the mass m and the gravitational acceleration g by the weight G in the equation, and write that I times omega times the time derivative of omega, plus m times omega times r squared times the time derivative of omega, is equal to G times r times omega. Because the right-hand side of the equation is equal to the torque tau z produced by the force F times the angular velocity omega, after dividing the equation by omega we obtain the expression stating that the sum of I and m times r squared, times the time derivative of omega is equal to tau z. Then we can express the time derivative of omega, that is the angular acceleration alpha, as the ratio of torque z produced on the rotating system by the moving weight to the sum of the moment of inertia I of the system, and the mass m of the weight times the square of the radius r of the spool attached to the vertical axle of the rotating system. This formula shows that the angular acceleration of the system is less than the value tau z over I derived in the previous description of the experiment. The difference between the two expressions is due to the fact that the weight g of the body suspended on the thread produces not only rotational motion but also accelerates the body itself. However, if the mass m of the body is 10 grams, the mass of the disks md is 50 grams, the radius r of the spool is 2 cm, and the distance d of the disks from the axis of rotation is 20 cm, then we can determine the angular acceleration by using the original formula. For these values, m times r squared is equal to 40 grams square centimeter, and the moment of inertia given by 2 times md times d squared is equal to 4 times 10 to 4 grams square centimeter. Hence we conclude that the ratio of the torque to the moment of inertia I is still a good approximation for the angular acceleration in this setup. As already seen, if no external torque is produced on a rigid body spinning about a fixed axis, then the body rotates with a constant angular velocity. Hence its angular momentum Lz with respect to the axis of rotation chosen as the z-axis, given by the product of the moment of inertia I of the rigid body with respect to the axis of rotation and the angular velocity omega of the body, is also constant. Its kinetic energy, given by 1/2 times the moment of inertia I, times the square of the angular velocity omega, is constant as well. We also demonstrated that if the moment of inertia changes in a rotating non-rigid system, then the angular velocity of the system also changes. For example, if a student sitting on a revolving stool already set in motion suddenly outstretches her arms holding a pair of weights, then she increases her moment of inertia and her spinning slows down. We used this experiment to demonstrate the law of conservation of angular momentum itself, stating that the product of the original values I1 and omega1 of the moment of inertia and the angular velocity is equal to the product of the new values I2 and omega2 of the moment of inertia and the angular velocity. Here the angular velocity omega2 can be expressed by the ratio of the moment of inertia I1 to the moment of inertia I2, times the angular velocity omega1. Nevertheless, the kinetic energy of the system does not remain constant, since the difference between 1/2 times I1 times omega1 squared and 1/2 times I2 times omega2 squared does not vanish. If we substitute the expression obtained for omega 2 into the second term, then we obtain 1 over 2 times I1 times 1 minus the ratio of I1 to I2 times omega 1 squared. As the law of conservation of energy formulated in the work-energy theorem telling us, this expression is equal to the work W of the internal forces, which does not vanish if the final moments of inertia I1 and I2 are different. For example, in the experiment shown in the photos, it is equal to the negative work done against the centripetal force by the student while extending her arms with the weights. We already mentioned that there is a formal analogy between the rotational motion like the one seen in the photos, and the rectilinear motion like a ball falling in the ground or oscillating at the end of a spring. If the rotation angle phi of the spinning rigid body corresponds to the linear distance x covered by the moving point-like body, the angular velocity omega of the rotation to the velocity v of the point mass, the torque tau z causing the rotation of the rigid body to the force Fx changing the state of motion of the point mass, and the moment of inertia I of the rigid body with respect to its axis of rotation to the mass m of the point-like body performing the rectilinear motion, then we can recognize this formal analogy between several equations. As formally established, the equation of motion of the rotating motion states that the moment of inertia I of a rotating rigid body with respect to its axis of rotation chosen as the z-axis times the second-order derivative of the rotation angle phi of the body about the axis with respect to the time t, is equal to the z component of the torque tau produced by the forces acting on the body, and it corresponds to the equation of motion of the rectilinear motion of a point mass m, stating that the mass m times the second-order derivative of the distance x covered by the point mass along a straight line chosen as the x-axis with respect to the time t, is equal to the force Fx acting on the point mass in the x direction. There is a similar correspondence between the expressions for the kinetic energy in the case of the two types of motion. The kinetic energy of a rotating rigid body is given by 1 over 2 times the moment of inertia I of the body with respect to the axis of rotation, times the square of the angular velocity omega of the body. The kinetic energy for the rectilinear motion of a point mass m has the same form. It is given by 1 over 2 times the mass m times the square of the velocity v of the point-like body. The work done in rotating motion and rectilinear motion has also its analog forms. The work delta W done during a small rotation of a rigid body is equal to the torque Z producing the rotation, times the angle of rotation delta phi, whereas the work delta W done during a small displacement of the point mass along the x-axis is equal to the force F producing the displacement, times the displacement delta x. In this table we summarize the quantities, expressions and equations which have formal analogies in the case of the two types of motion. The left-hand column of the table shows quantities and equations describing the rectilinear motion of a point mass or a particle-like body along the x-axis, whereas the right-hand column contains the corresponding expressions for the rotational motion of a rigid body about the z-axis. In the first line we specify the fundamental kinematic variables for the two kinds of motion, the Cartesian coordinate x measuring the distance covered by a point mass moving along the x-axis for the rectilinear motion, and the polar angle phi measuring the angle of rotation of a rigid body about the z-axis. The derivatives of these fundamental kinematic variables with respect to time are the velocity vx of a point mass along the x-axis, and the angular velocity omega z of a rigid body rotating about the z-axis. Similarly, the acceleration ax of a point mass along the x-axis is defined by the time derivative of its velocity vx, that is the second-order derivative of its coordinate x with respect to time, and the corresponding quantity is the angular acceleration alpha of the rotating rigid body defined by the time derivative of its angular velocity omega z, that is the second-order time derivative of its rotation angle phi. The fundamental property of a point mass performing a rectilinear motion from the viewpoint of dynamics is its mass m, and this property for a rotating rigid body is the moment of inertia I of the body with respect to the axis of rotation. The later can be written as the sum of the product of the point masses mi approximating the body and the square of their distance di from the axis of rotation. The effect changing the state of motion of a point mass traveling along the x-axis is represented by the force Fx acting on the point mass in the direction of the x-axis. The corresponding quantity for a rigid body is the z component of the torque tau with respect to the axis of rotation causing for the body to rotate along the fixed z-axis. As we have already seen, the corresponding equations of motion tells us that the mass m of the point mass times the second-order time derivative of the x-coordinate is equal to the force Fx acting on the point mass in the x direction, and that the moment of inertia I of a rigid body times the second-order time derivative of its angle of rotation phi is equal to the z component of the torque tau rotating the body about the fixed z-axis. Another fundamental dynamical quantity describing the rectilinear motion of a point mass is its momentum or linear momentum p in the x direction defined by the product of its mass m and its velocity vx in the x direction. Its corresponding quantity for a rigid body rotating about the z-axis is the z-component of the angular momentum L of the body with respect to the z-axis, which is the product of the moment of inertia I of the body with respect to the axis of rotation and the z-component of the angular velocity omega of the body. The law of conservation of momentum tells us that the time derivative of the momentum px of a point mass in the x direction is equal to the force Fx acting on the point mass in the x direction. Its analog is the law of conservation of angular momentum, stating that the time derivative of the z-component of the angular momentum L of a rigid body rotating about the z-axis is equal to the z-component of the torque tau produced by the forces acting on the body. We also defined a quantity called impulse for a point mass under the influence of forces by the integral of the force Fx applied on the point mass in the x direction with respect to the time t from the initial time 0 to a given time tau. This definition can also be introduced for a rotating body in the form of the angular impulse acting on the body, which is given by the time integral of the z-component of the torque tau over the time interval from 0 to tau. We have already shown the correspondence between the concept of infinitesimal work done during the two types of motion. The infinitesimal work dw done on the point mass by the force Fx acting in the x direction for the infinitesimal displacement dx of the point mass is equal to Fx times dx. Similarly, the infinitesimal work dw done on a rigid body by the torque z rotating it through the infinitesimal angle d phi is given by the product of tau z and d phi. By applying these equations we can also express the power for both kinds of motion. The power p of the force Fx acting on a point mass traveling with the velocity vx along the x-axis is equal to Fx times vx, whereas the power p of the z-component of the torque rotating a rigid body about the z-axis with the angular velocity omega z is given by tau z times omega z. The formal analogy between the kinetic energies for the rectilinear motion and the rotating motion is already shown as well. The kinetic energy of a point mass m is defined by 1 over 2 times the mass m times the square of the velocity vx of the point mass moving in the x direction. The same quantity for a rigid body rotating about the z-axis is equal to 1 over 2 times the moment of inertia I of the body with respect to the z-axis times the square of the z-component of the angular velocity omega. We can also mention Hooke's law in the case of the one-dimensional motion of a point mass attached to a spring, stating that the restoring force Fx acting on a point mass is proportional to minus its displacement x measured from its equilibrium position, where the proportionality factor k is the spring constant. We can generalize Hooke's law to the z-component of the torque produced on the rigid body by directional forces, and state that tau z can also be proportional to minus the angular displacement phi of the body about the z-axis, where the proportionality constant k is the torsional constant. The corresponding period t measured for a point mass m oscillating under the influence of forces following Hooke's law is given by 2 pi times the square root of the ratio of the mass m to the sprig constant. Similarly, the period t of the oscillation of a rigid body about its axis of rotation can be written as 2 pi times the square root of the ratio of the moment of inertia I of the body with respect to the axis of rotation to the torsional constant k. Let us consider a more general mathematical description of rigid rotation about a fixed axis, where a Cartesian coordinate system is attached to the axis of rotation such that its origin is located at the reference point O on the axis, and its z-axis is the axis of rotation. In the study on the mechanics of systems of point masses, we saw that the momentum of a rigid body approximated as the composition of mass elements, that is a rigid system of n point masses, can be written as the sum of the momenta pi of the individual point masses mi. That is the sum of the mass mi times the velocity vi of the point mass mi from I equals 1 to n. We also saw that the angular momentum L of the rigid body in such an approximation can be written as the sum of the angular momenta Li of the individual point masses mi, that is the sum of the mass mi, times the cross product of the position vector Ri of the point mass mi with respect to the reference point O and its velocity vi from I equals 1 to n. Similarly, the torque tau produced on the rigid body by forces acting on the body can also be expressed as the sum of the torques tau I produced on the individual point masses mi by the forces acting on them, that is the sum of the cross product of the position vector Ri of the point mass mi and the net force Fi acting on the point mass from I equals 1 to n. We already determined the scalar components of the momentum, the angular momentum, and the torque in these vector equations. Since the velocity vi of a rotating point mass mi is equal to its distance di from the z-axis times the angular velocity omega of the rigid body, the magnitude of the momentum pi of a rotating mass element mi is given by the mass mi times the distance di, times the angular velocity omega. This expression for the magnitude of the momentum pi can be used to determine the Cartesian coordinates of the momentum vector as the projections of the vector on the coordinate axes. However, we can also use a cylindrical coordinate system with the same z-axis due to the rotational symmetry of the motion. In this case, the distance di is equal to the radial coordinate ρ of the cylindrical coordinate system as seen in the expression in the second line of the right-hand side of the equation. The different components of the momentum can be derived by projecting the momentum vector of this length onto the axes if the polar and azimuthal angles that describing the direction of the vector are known. The z component of the angular momentum Li of the point mass mi was also derived by applying the same procedure, where we use the relation stating that the distance di of the point mass mi from the axis of rotation is equal to the length of the position vector Ri of the point mass, times the cosine of the angle theta I measured between the direction of the position vector and the z-axis. As a result, the z component of the angular momentum Li was written as the mass mi times the square of the distance di, times the angular velocity omega in Cartesian coordinates. In a cylindrical coordinate system, the distance di is replaced by the radial coordinate ρ, as seen in the second line. The other components of the angular momentum Li can be determined as well by projecting its vector onto the x and y axes and using trigonometric relations. Similar projections of the cross product of the position vector Ri and the force Fi gives the components of the torque tau I in the Cartesian and cylindrical coordinate systems. The rotation of a rigid body about the z-axis is determined by the components of the equation of motion stating that the time derivative of the angular momentum L of the body with respect to the z-axis is equal to the torque tau produced by the forces acting on the body. This vector equation representing the law of conservation of angular momentum consists of three scalar equations describing a motion with the degrees of freedom reduced by the constraint fixing the axis of rotation. The components of the vector equation are written both in Cartesian and cylindrical coordinates. We saw that the z component of this equation in the green boxes for both types of coordinate systems describes the rotational motion of the body about the z-axis. In Cartesian coordinates, the two other components of the equation of motion are its x and y components, whereas in cylindrical coordinates we have the radial and azimuthal components of the vector equation denoted by the subscripts ρ and phi, respectively. The constraint forces exerted on the ball rings fixing the direction of the axis of rotation and the torques produced by the constraint forces can be determined from the other two components of the equation of motion shown in the yellow boxes, plus the law of conservation of momentum, where the later states that the time derivative of the momentum p of the center of mass of the body is equal to the net force F of all the forces, that is both the free and constraint forces acting on the body. By expanding the vector equation of the law either in Cartesian coordinates or cylindrical ones, the scalar equation can be arranged in the same group as the equations of the law of conservation of momentum shown in the yellow box. These five scalar equations written in both types of coordinates are called the kinetostatic equations of the rigid rotation, and they are used to determine the constraint forces and the torques produced by them. As the figure shows, each point of the rigid body rotating about the z-axis moves along a circular trajectory in a plane perpendicular to the z-axis, that is all the point masses approximating the body perform a planar motion parallel with the xy plane in the Cartesian coordinate system. Then the z component of the momentum p of the rigid body vanishes and so does its time derivative in the law of conservation of momentum, which tells us that the z component of the net force F acting on the body is equal to 0. The latter indicates the balance between the free forces and the constrained forces fixing the position of the rotating body in the vertical direction.